Hi, good morning. Welcome to this morning's talk on guest MFD's unmapped potential. This talk will be a status update on the recent and upcoming patch series. So I'll dive into it. I'm Ackerley. I'm from the confidential computing team at Google Cloud. And I've been working on this presentation together with Fuad, who's on the pKVM team on Android. So this conference was supposed to be the first time I'm actually meeting him in person, but unfortunately he's unable to be here in person. And he says he'll be giving me moral support over live stream. So as a recap, guest MFD is guest first memory. And with guest MFD, we are able to allocate guest memory that is not accessible to the host. So by not accessible, we mean that the host cannot map this in the host page tables. So in contrast to traditional mem slot configuration where a user space address returned from an mmap call is used, we will instead be using a file descriptor and an offset for the guest memfd when configuring KVM mem slots. Guest memfd was originally built for Cocoa VMs like TDX, Ceph, and SMP. And it was built because for Cocoa VMs, a host attempting to access guest private memory could result in a host crash. And so that's not something very desirable. And so the value proposition for guest memfd is that without any host mappings at all, this problem is solved because with no mappings, then there cannot be any accesses from the host. While it was originally meant for Cocoa VMs, the long-term vision for guest memfd is to use it for all guest memory, regardless of whether it's Cocoa or non-Cocoa VMs. So there's a common saying that a problem shared is a problem halved. But in this case, at least up to Linux 6.16, guest memfd memory is not actually shared. So let me illustrate that. So if this is a KVM mem slot, these are the two fields that we are mostly interested in. And as of 6.16, struct gmem is configured to point to a guest memfd. And this private page is from like one place in physical memory. And then user space address is configured to point to another place in shared memory. And so as an example, we can use anonymous memory for this. So it's just a completely different memory from guest memfd. When the guest does a private access to memory, KVM will look up struct gmem and then go to the guest memfd instance and then look up the physical page using the offset, FD offset. And for a shared access, it will instead look up the user space address. And because it was previously configured as from anonymous memory, it will get the memory from a different place for the guest. But in some cases, we actually do want in-place sharing of memory. So there are some hypervisors like Gunya and pKVM that protect guests only using MMU-based protection. So the stage 2 page tables are configured with extra permission stuff, and the guest memory is not actually encrypted at all. So in this case, if we were to have a separate backing memory for shared and private memory, then conversions would require a massive amount of copying, which is inefficient and basically just wasteful. So in-place shared to private conversions becomes a requirement in this case. And because we want to also support non-Cocoa VMs, and we want to support everything that VM would normally do with a user space address, shared memory must be mappable and guppable by the host. But even with this in-place sharing, we must still uphold the original intent of guest memfd, which is that guest private memory should never have valid mappings in host user space. So with this sharing, we would be configuring the struct gmem to point to an FD and offset within guest memfd. And the user space address should also point to that same page with mmap. So this is one of the most recent patch series for guest memfd, which is led by Fuad. So with this, we are enabling Mmap for guest memfd. This patch series allows Mmap of guest memfd for non-Coco VMs on x86 and ARM64 platforms. And when this Mmap flag is set, all memory in the guest memfd instance is shared. So by default, if we don't specify the flag, all memory is private. So the same guest memfd instance can still be used for the existing use cases, which are like for Coco VMs. And if we set the flag, then it can only be used for non-Coco VMs. At this stage, there's still no support for huge pages or migration. But it does allow, with this, we have non-Coco VMs can start using guest memfd. So actually, the main point of this patch series is to unblock all the good stuff, which we will talk about in a later slide. The status of this is that it's now in KVM next, and it should be ready for 6.18. So these are some of the upcoming patch series that Mmap unblocks. So the first of which is direct map removal support, which Patrick will be talking about immediately after this talk. So I'll leave that in. And there's also NUMA man policy support for guest memfd led by Shivank. Mmap unblocks this because Mmap returns a user space address, and the current ways of configuring NUMA man policy support using Mmap Vice, I believe, relies on the user space address. So with Mmap, we unblock this second patch series. And for there are two more patch series, in-place conversion support, which Fuad and I are working on, as well as huge page support, which I'm working on. So just now, I mentioned that we do one in-place conversion support. And that's because at the moment with the Mmap patch series, at this stage, it's basically all or nothing. So either the entire guest memfd instance is shared and mappable and used by non-Coco VMs, or the entire guest memfd instance is private, not mappable, and used for Coco VMs. So we would actually like to share and unshare specific pages of the VM's memory at runtime, at guest runtime, and dynamically. And this is usually triggered by the guest sharing with the host. Even while supporting all this dynamic sharing and unsharing and shared to private conversions, we must still uphold the original intent of guest memfd, which is that guest private pages must still never be met to host user space, page tables, and not even transiently. So in order to enforce this, guest memfd will track the state of each page in memory. So we want to track whether it's either accessible by all as in guest and host, or shareable only to the guest, as in owned by the guest, and only guest accessible. Status is that we had a few RFCs, and the next RFC will be posted soon after this conference. As for huge page support, we are interested in this because huge pages bring performance benefits in the form of shorter page table walks on TLB misses, and ideally there should be fewer TLB misses. In addition, if we take huge pages from huge TLB, then we also gain huge TLB VMAP map optimization, which is 1.6% of the memory. So 1.6% sounds like a small percentage, but actually for a huge VM, it can come up to gigabytes of memory, which is really valuable to us. So for non-confidential VMs, we can already get all these benefits by using huge TLB directly as the backing memory. And we want to bring all those benefits to guest memfd for Coco VMs, because Coco VMs can only use guest memfd. And so even though this entire effort of huge page support works for both Coco and non-Coco VMs, it's mostly catalyzed by Coco VMs. However, using huge pages brings about its own set of problems, because what if a guest wants to share just one page within a private huge page? So let me illustrate that. So this guest has a private huge page, and it wants to share just one page within that huge page with the host. So the immediate thing that comes to mind is that we would just punch a hole in the huge page. But if we punch a hole, this space can actually, it can't actually be used by anybody else, because if it's used by someone else, then we are just introducing fragmentation into this huge page, because we cannot guarantee that that page will be freeable at the same time when we are done with this huge page. Yeah, so for at least at 6.16 right now, we are allocating the shared page from somewhere else and using that to back the shared memory. And we have this space in the private huge page that is unused, but we can't really do anything with it, like a non-freeable void. So as you can tell, this introduces significant overhead. So for every page that's shared, we have 2 times the amount of memory. And for a malicious or like otherwise broken guest, it could start using a lot of memory, up to twice the amount of memory that the guest was paying for. So with in-place conversion, we can achieve something like this, which is that the non-freeable void is now reused as the shared page. For huge page support, we are going to be using, this is an overview, we'll be using huge TLB pages to provide huge pages for guest MemFD, and we'll be playing nice with the rest of huge TLB. So we'll be respecting all the quotas and reservations and pools and subpools. These huge pages can be mapped into stage 2 page tables at up to 1G mapping level, and in the host user space page tables at up to 4K mapping level. And to achieve this, we'll be splitting the huge page at runtime on conversion to shared, and we try to merge on conversion to private. We do this splitting to track users of each shared page, and we want to do this because we want to play by core MM's rules. So each of the pages have a ref count, and we are going to use that same ref count so that everything that used to work with non-confidential VMs still works with confidential VMs. And we also do this splitting to limit core MM from mapping beyond the shared ranges. And finally, when released from guest MFD, we'll be merging the folio, like taking all the split shared struct pages, merging them, returning the entire thing to huge TLB. So here's a list of references for anyone who's interested, and I'm ready to take questions. And thanks for coming to this talk.